Okay, when we last left off, we were talking about enzymes. We're using these free energy diagrams. Okay. And the whole idea that the catalyzed reactions just decrease the activation energy of the limiting step. Well, technically, it was many times it's a single step reaction. And we had something like this before. So, for example, on the simplest scheme, or it's not the simplest, but on a simple scheme, perhaps, if I can get it to right, we have E plus substrate. You always have to have binding that occurs to make what we'll find out later is also called the Michaelis complex. We're going to do what I call what's often called the chemistry step, which is where it converts the substrate to product. And notice this is one time when there's only one substrate and one product. And A plus B. Some of the other vernacular that gets used for, and this is very, very important in biochemistry in particular, but is the letter K. It's used for both kinetic rate constants and also equilibrium constants. You have to use the correct K. If it is a capital K, that is a thermodynamic constant. So that's like an equilibrium constant. Okay. Whereas a lowercase k, those are kinetic rate constants. This is a little thing. Another thing that they also do, and I don't know that your book tells you this, they may just assume that you know it, is so each rate is going to have a little k, and each one's going to have a capital K too. But the way that the nomenclature that they use, for example, this first step, going the forward direction, it's lowercase k with a subscript of 1. But going backwards, like going from ES to E plus S, it's a lowercase k with a subscript of -1. So it's going the opposite direction. So just like the second one would be K2, K minus 2. We don't say -2, we say -2. K3, and K minus 3. Okay, that's going to be important later on. Whereas equilibrium constants would be capital K's. And you can put them in terms of little k's, but we'll get to that later on. All right. So we're doing free energy. Once again, if this was the uncatalyzed reaction. Whoop. Okay, so we had substrate here, we had product over here. Okay, and that's going to go on down. All right, so all of these minima would be where we have those intermediates, ES and EP. I'll give you a moment to get caught up. I deliberately drew it differently than the way I drew it on my date. I don't like the figure in your book. So that's why I'm trying to give you multiple figures. And technically there would have been an E. E plus E. You know, you get your enzyme back. Of course, this is energy, this is reaction coordinate, or time, or whatever you want to call it. So the first step, so if I'm going to walk you through it, we have binding. You always have to add some energy. It takes some energy to get to bind. Then it's presumably more stable. Well, I should say more stable than it was here. And each of these would be a transition state. Come on now. Each of these are a transition state. And so they could even call that step 1, like transition state 1. Use a different one if they wanted to. Transition state 2. Transition state 3. Okay. But we had binding, we got ES. We did chemistry, okay, and we got EP. And then we get product release. So going in the forward direction, going that way, what is going to be the rate limiting step of those 3 steps?
Chemistry step.
It's still going to be the chemistry step, okay? And the way that we get that is you just measure from the bottom of the minima to the top of the hill. So there's that one, and then we have from here to there. And then for the third step, it's there to there. Going backwards, what's the rate limiting step? Because in theory, enzymes, remember, they catalyze the same frontwards and backwards. In theory. What would be the rate limiting step if it's for the backwards reaction? And we're going to find out in vivo, there really are important reactions that go both ways, frontwards and backwards. Otherwise, you would die. But what's the rate limiting step going backwards? It's the binding step, most likely a product. See, for it to go back, what we're calling product. This is probably the biggest hill to climb, and then this one, and then that one's relatively small. Okay, and so that's why I wanted to do this to let you know that, first of all, the minimum don't have to be the same, the maximum don't have to be the same, and the rate limiting step going one direction is not necessarily the rate limiting step going the other direction. Okay, and so, and like I said, in vivo, this is important. And we'll talk a little bit about some of this. Once again, if next semester you're interested in, especially this with respect to medicine and all that kind of stuff, then we do have an enzymology class that we'll be offering. Okay, so an example that I gave here before, I did put the ES slightly lower, but the overall change was going to be lower, okay, between the catalyzed and the uncatalyzed reaction. That is a possibility, by the way. This is the figure that I think is the most recent edition of the book as well. I don't like it because all of them look about the same, at least to me. They kind of show you that it's a little different, like ES and EP are the same and blah, blah, blah. But in reality, they could be almost anywhere. And I wouldn't be surprised if on a quiz or something that you had, or an exam, you had something where you had to try to label these or talk about rate limiting steps and equate that. Okay. Just like it's not always true that product is lower energy than substrate. That's not always true. You know, sometimes it's higher energy than substrate as well. And so it's just that, I don't know, it's an oversimplification here. Okay. So this shouldn't be brand new. I hope that you had heard about these before. But there are 2 models that have been proposed for enzyme catalysis. One's called lock and key, one's called induced fit. Lock and key is the easiest one to explain, because what it says is that the binding site, essentially on the enzyme, looks just like the substrate, which fits in like a lock to the key, and so it's called complementarity, and therefore that's how it binds and it does chemistry. It gets like the substrates and everything there in close proximity, and they would work. Induced fit says that the binding of a substrate or binding of something causes the fit to change, the conformation to change, that results in the complementarity. Okay. So, which of these is correct? Or are they both? Is it all in? Something smells really good. It smells like cantaloupe. Which I'm allergic to cantaloupe. If you see me starting to break out in hot, no. All right, so which of these is correct? Neither. Well, it's not cut and dry, okay? So for some, it may have some similarities to lock and key, but not quite. And I'll explain the reasons why lock and key doesn't work. Just a moment, mathematically at least, show you. Induced fit doesn't, not everything does the exact same thing induced fit. Induced fit is probably more correct in the broader scheme of things, but it doesn't necessarily explain every single enzyme. In fact, there's something called transition state theory that they use when talking about a lot of enzymes, and it seems to work well with describing most enzymes. Okay, and so this is blown up wrong. Okay, each one. So we're just gonna look at. This is the comes from the book. I don't know why they did this. It's supposed to be like a decomposition, like a cleavage reaction. And so what they say is that imagine your substrate and your product is going to be two pieces, so it's just breaking two. So then the transition state would be when it's bent. Okay. And so they show the uncatalyzed, everything is even. But we have to just remember, like, this is a transition state, which is kind of weird looking. I don't know, but like what it would be. So nothing new here. I'll tell you something. Well, this is what would be the lock-in key. It says that the binding site would be complementary to the substrate. Well, the reason why mathematically that doesn't make sense for the most part, and this is where I know I've had lots of people that have gotten confused, like, where did magnets come from? That's supposed to say, I wouldn't have drawn it that way. I would have shown you like an example of like a protein or something, where you can imagine the magnets being like hydrogen bonding, or like, you know, positive charges binding to negative charges, and so they're just showing you that there's something there that's attracting the binding of the substrate. And if you notice, the binding site of this substrate is complementary to its shape. Well, what that does is, since it's so happy there, it's going to make the energy of the Michaelis complex, this ES complex, really low. It's happy. It's nice and snug. You know, it reminds me of putting, you know, my baby in the swaddler. So he likes being swaddled. It's like that. So the energy, yes, it takes some energy to stick it in there, but then it's so comfortable, for lack of a better word, do that complementarity of the ES of its shape, that it's much lower in energy. In fact, what you've done is you've made the reaction even less likely to go. See, now it's even bigger hill than it was before, since the ES complex is lower than the substrate complex. Okay. Oh, righty. Now, if you notice on the example that I gave before, let me see, let me just double check. Whereas if you do something that's more of an induced fit, this is really the idea of transition state theory. Transition state theory states that the binding site on the enzyme is complementary to the transition state. So whenever it goes into bind, yes, it takes a little bit more energy maybe for it to actually bind, but it's already halfway there, it's already halfway bent. So that's why it makes it easier for it to break apart. Okay, so that's why this is the transition state theory, an idea that the binding is complementary to the transition state. Instead of it looking like the straight bar, when it binds, it has to bend already. And by bending already, it makes it more favorable for it to break. Okay. Many times in real life, what it does is it's binding the substrate in such a way that the nucleophile can come in and attack more easily. Okay. So if you remember back to Gen Chem, you probably, if you think way back to Gen Chem, or maybe it's I like when it was covered organic as well, for like substitution reactions or something where you're going from like a tetrahedral to the trigonal planar look to back to the tetrahedral, or tetrahedral to the pentavalent, the one that has 5, back to tetrahedral. It makes it look like that middle already. Okay. Oh, so this is just an example to show you what catalase can do, and what catalase does in vivo is it breaks down hydrogen peroxide is a natural byproduct of chemical reactions, and it breaks it down to harmless water and oxygen. And hydrogen peroxide is actually better than some of the other reactive oxygen species that are out there because of the fact that we have catalase around. And so it just shows you that without any type of catalyst in vivo, what the activation energy would be. And then they call that relative rate 1. Then if, in organic chemistry, you learn about platinum, all that kind of stuff. But if you do that, you actually do get a decrease. And it increases the relative rate by 10 to the power 4. Okay, so it's much faster. However, in vivo, we can't put platinum in us, right? So we have catalase, and catalase lowers it considerably and increases the relative rate, the kinetic rate constant, So much so that we're now talking in the order of 10 to the power 8. Okay. These are just some of the other examples where you can have really huge changes. Okay. So some of these we actually talk about next semester. Some we won't. Okay, but yeah, if you look at aridine monophosphate decarboxylase, I mean, it's a huge enhancement. Okay, what kind of enzyme, what do you suppose is happening with decarboxylases? Forget all this aridine monophosphate. What do you suppose decarboxylase is going to do? Just to kind of review. You don't tell me decarboxylates. That's that world piece. What do you suppose it's going to be giving off? If it's decarboxylating, what's a carboxylate look like? COO minus, right? So if you're going to remove that COO, what do you suppose is going to come off as? What's one of the products going to be? Don't overthink it.
Carbon dioxide.
Carbon dioxide, yes. That's what it's going to give off. Decarboxylases give off carbon dioxide. This should make sense. Every enzyme is going to have an optimal temperature, just like it's going to have, typically will have optimal pH as well. If you increase the temperature, the rate's going to go up until you get to this optimum. So you always see this kind of bell curve. And then it's going to go down because at some point in time, sometimes it kind of flattens for a while and then it goes down. At some point in time, it's going to start to denature the enzyme. Okay, even if it's an RNA or protein, it doesn't matter. It's going to be denatured. Okay. There we go. Ooh, this got cut off. Okay, I've already been saying this without saying this. With saying this exact words. But many times, the binding energy that's used to make ES is just one step for the entire process. So that's why I've been talking about, we have the binding step, we've got the chemistry step, we've got the product release step. Sometimes you have even more steps than that. Okay? And so it can just be one factor towards the actual process. Typically, you're going to have one rate release step, that's the slowest step, the biggest hill to get over. Okay? Now, what happens, once again, is that the binding is going to make it to where catalysis is more likely to occur by putting together the nucleophiles and electrophiles where they need to be, like in the right geometry. But there are multiple ways to do that, multiple mechanisms. Sometimes it does require a covalent interaction with the enzyme, but it must be transient. What does that mean? It involves a transient covalent interaction. What does transient mean? What? It doesn't last. It's not that it's homeless, but it just doesn't last. So it has to be only for a short period of time, because otherwise the enzyme would be irrevocably changed. In fact, some drugs are what's called suicide inhibitors, to where they make a covalent interaction with the enzyme at the active site, and it's not transient. And so aspirin is one of those. And aspirin is technically a suicide inhibitor. It goes and binds a COX enzyme, and it makes a covalent interaction that our body doesn't break down, and so that enzyme is dead. Okay, hence the reason why it's called suicide inhibitor. So, what are the types? Every year I think I say I'm going to change this slide and I don't. I forget, I go home and forget. Specific acid-base catalysis should not be under general acid-base catalysis. Okay, so if you're making your own outlines, like if I was going to do that big one, I would just say acid-base catalysis, and we have specific and general. Does that make sense? Does it make sense? General, specific, general. Acid-base catalysis just means you're using an acid or a base. It's like yin and yang, you can't have one without the other. You already know that there's conjugate acid to the base and conjugate base to acid. If it's specific, which doesn't happen very usually in vivo, what that means is it specifically involves a proton, hydrogen, or hydroxide anion. And hydroxide anions are around a whole lot. Okay, right? We don't just take sodium hydroxide. So that's why it's not as often as what's called a general acid base. Typically, general acid bases utilize something other than that. Okay, we're talking things like, for example, what's one of the amino acids that could act as an acid for its R group? That acts as an acid? It can. So we could have histidine, because what do acids do typically? They donate the proton. So if we're going to do histidine, that wasn't the one I was thinking of. It's actually a really good example. I'm only going to draw the R group. So let's say that this, remember, there's always a linking carbon, people. Okay. I didn't draw it very big. One of the nitrogens, and it doesn't matter which one of the nitrogens is going to have a hydrogen on it at all times. So then we can imagine, and whereas the other one could be lone pair electrons, if it's at the right pH, then that second nitrogen would also be protonated, and therefore it would be a positive charge world. But this is on the enzyme. This is on the inside of an enzyme. Inside of an enzyme. It just didn't sound right in my head. Okay. We can imagine it being a general acid. What hydrogen, don't overthink it, what hydrogen does it have that it can donate? The one on the left, right? Because technically there are hydrogens on the carbons, but carbons do not, as remember from organic chemistry, they don't, or organic for that matter, that carbon to hydrogen bond is not polar enough for it to be able to donate and give freely, okay? And so, yeah, there's only the one. So that's why. So we could imagine something else coming that has lone pair electrons. I mean, it doesn't really matter whatever it is. I'm just going to call it X, but this is not a halogen, okay? But it has lone pair electrons where it can come and it can take that hydrogen. And in doing so, that histidine now is acting as a general acid. Does that make sense? Likewise, histidine can also act as a general base. So histidine is interesting then, because a lot of times in the same mechanism, a histidine will act as both. You can't get that a lot of other things. And the reason why, I'm just going to show you this one. That's why I'm surprised that you get. Usually we build up to histidine. But we can imagine these electrons have to go somewhere. So they go down here, boom. Sound effects optional. We can't leave it alone, because now this carbon, which does have a hydrogen on it, which is not shown, which is implied, would have too many electrons around, it would be negatively charged. That's bad. So something has to break or leave or whatever. What do we have on that carbon that can break or leave? The double bond. Okay? And so what happens is this double bond can then swing out and many times then go and attack something. And let's say, for example, that it goes and attacks. This is just one example. This is a good review, because this does happen in vivo all the time. A hydrogen hanging off of a neighboring amino acid in a three-dimensional structure. It's supposed to be okay. So it's taking that hydrogen. So now it's a general base as well as being a general acid. One side of the histidine is acting as a general acid by donating the hydrogen. The other side is acting as a general base by swiping the hydrogen. Okay. What amino acid did I draw that got swiped? Serine. That's why it sounds good to you. This actually is the kind of mechanism that happens, by the way, for a lot of the proteases. Okay, those, in fact, there's a whole class called serine proteases, and this is the mechanism. Many times the X here is in aspartate. Does that make sense? Because aspartate becomes aspartic acid. It takes the hydrogen off of the histidine. In fact, this is called the catalytic triad. It is not some type of Japanese yakuza, crime lord. But let that sink. Maybe. All right. But no, what happens is you have this aspartate. Well, let me use that way it's on the video. And you have this aspartate, which would be carboxylate here, which comes and takes the hydrogen, becomes an aspartic acid. And then we have the electrons, boom, sound effects optional. These electrons in break to take this hydrogen off. The whole reason to do that is this would be the result. I didn't leave myself much room. Ooh, that was really freaky. That is so awesome. Takes a little to amuse me. Okay, so I'm going to draw, because this is actually really going ahead, but not too much. All right, so the result here would look like this. I'm now going to go ahead and draw in, instead of X, I'm going to draw in the aspartate. But remember, it's got the hydrogen that had been hanging on the, I even got the right color, right? So that had been hanging on the histidine. This is the histidine that's nearby. And it's got the hydrogen that had been on the serine. And then we have the serine. What will the serine look like? Think back to organic chemistry. What will it look like after it had its hydrogen taken away? It's not an aldehyde. What's it called? What's missing? So if we go back here, I'm just going to do this last step. This swings out, takes that hydrogen, but takes it as a proton. Remember, it's a proton. These electrons have to go somewhere. They're going to be staying here, the way I have it drawn here with this oxygen. So therefore, where are they at right here? Don't overthink it. Matthew Scales, where's it at? Where did those electrons go? I haven't drawn them in yet, so where are they? Or where should they be, I should say? Around the O. That's why I say don't overthink it. It's around the O. So what is this? This isn't an aldehyde. Because what makes an aldehyde an aldehyde? A carbonyl group. So what is this? I'm missing something else here, by the way, that you might say half of a point. What am I missing around that oxygen? Charge. Okay. So I've converted the serine into what kind of compound? What's it called? When it's no longer an alcohol, it's lost its hydrogen, it's called. It's negatively charged. So what are the endings for negatively charged things? There's Ace, like carboxylate. It's another one. Think about it. Sodium. I. Okay, that's it by the way. Just H, I, and I. It's not I. Okay? So what an alcohol becomes not an alcoholide. That sounds funny. What is that called? What is that functional group? It's really important. Yes. I'll put it together. What did you call it? Oxide. It's an oxide. What kind of oxide? It was an alcohol. Becomes what? Alkoxide. There's a whole section in Organic Chem 2. You should have covered that in Organic Chem 2. These are now alkoxides. Alkoxides were alcohols that lost their hydrogens. Okay, but they're amazing nucleophiles. Okay, so that's what that's showing. So that oxygen can go and do the attacking. All right. So that's just an example of general acid, general bases. For example, you can have any of the alcohols can become a general acid, right? Because they convert the hydrogen. Possibly the carboxylic acids are amazing general acids, and their carboxylates would be amazing general bases. Histidine is. You can have arginine and lysine, because since they can be positively charged, they can take the hydrogen and give it away under the right conditions. So things like that. Another method that's used is called covalent catalysis. Covalent catalysis is just like the name implies. The enzyme in the mechanism itself is going to form a covalent intermediate. Okay. Please note, these are not mutually exclusive. For example, the serine protease I've been talking about that I just drew up here, it actually, during the entire mechanism, goes through both the general acid, general base, the part that we've shown, but then that alkoxide is going to go and do the attacking against the protein that it wants to break down. That's what proteases do, they break it down. That's a class of enzymes. Proteases break down protein. And it forms a covalent intermediate. So see, it has both those mechanisms, and they are not mutually exclusive. And then we have metal ion catalysis, which is the most difficult to explain usually. What do you suppose it's going to involve? Metal ions. And the reason why I say it's difficult sometimes to explain because you guys don't take inorganic chemistry. So the only exposure to metal ions that you've had typically is through chem. But metal ions themselves can perturb the local pKa's. So for example, you can have metal it's called chelation, that chelates to a water, and in doing so will make the oxygen of the water more nucleophilic. This is one example. But it just means that the metal ion is used to ultimately alter the what is the nucleophile molecular. Okay. Alrighty. This right here, I'm going to go really fast because it's review. Really fast. It should be review. This is just generic mechanism. A plus B is going to make product. You always have to have what's called a rate law. The rate laws will always will have like rate, V or nu, technically a lot of times, technically they usually like to use nu, is equal to, they always have to have a lowercase k, that's a kinetic rate constant, see, k. Sometimes they write out rate. And then the rate law for the forward direction is going to be equal to the concentration of the substrates, oops, not AA, substrates to some power, okay. And here, that's where I'm going to call it X and Y, but they used, what, F and G or whatever. Specific rate constant, kinetic rate constant, those are used interchangeably. The order of the reaction literally is just adding up the exponents. So if you have something that looked like this, okay. So the rate is equal to K, always K. No, I will, pretty much every year I have at least one person that will forget to put a K in there. Times A times B squared. So the order of the rate for this reaction, the order of the reaction for this rate law, what will it be? What's the sum of the exponents? 3. By the way, it's called a termolecular. Not turd molecular. But termolecular. But yeah, it's 3. Alright, which once again you should have covered that in organic chemistry and then Chem 2 and lots of things. So this is just showing the same thing. You can have a second order, for example, when A times B, or if it was just K is equal to, rate is equal to K times A squared, it's still a second order rate constant. What that means is in the rate limiting step, 2 things are happening to react together. Usually in vivo, you just have 0 order, which is weird, and we'll talk about that in a moment. 0 order, first order, and second order are the most common. Once in a big while you'll hear about a termolecular reaction, but it's very rare. Usually 0 first and second order. Just like you want to, if at all possible, manipulate the math down to get to 0 or first order. Okay. As I will tell you, this is the part that uses calculus, but I don't usually, you just do it. And it's not that bad. People make it calculus out to be a lot worse than what it really is. If we're doing a zero order rate reaction, it just looks like this. Oh, whoops, I thought it was down here. Nu is equal to K times whatever, A, to the 0 power, right? Well, what's anything to the 0 power? 1. So it's really nu is equal to K. And what that means is it doesn't matter what conditions you're at, the rate is not affected by substrate. And that does happen in vivo, and I'll show you in a moment like how that can happen. Okay. I mean, they give you the example right here, but that may not mean a whole lot to you right now. Concentration reactions, enzymes, something, blah, blah, blah. Ooh, that kind of goes above that. We'll talk about it. Okay, remember we use E plus S, goes to ES. Many times, not always, but many times, if it's one substrate, one enzyme, that first step, that first rate is going to be a second order rate constant, right? Because you have two things coming together. You can manipulate it in order to make it, say for example, where the concentration of E is so high that the ES is really, really tiny. So therefore it only remains on S, or vice versa. Concentration of substrate is so high that it's only dependent upon the concentration of E. This is aspartate transcarbamylase. It's involved in biosynthesis DNA and RNA. I don't know that we'll get to actually go over this enzyme in great detail next semester, just because I bet due to time constraints we probably won't get to do all of biosynthesis nucleic acid. But this is carbamoyl phosphate. Carbamoyl is probably a functional group that you guys did not talk about a whole lot. It's an amide that only has one carbon. So if you notice, it's a carbamoyl group. And then phosphate. And it adds it to aspartate to make N-carbamoyl aspartate. The reason why is if we look at this, it's ugly. Okay, but first of all, just in case you hear me use these terms, this is called a lag. See, it's a little bit sigmoidal. See, it's a little bit S-shaped here versus being hyperbolic. Hyperbolic is so nice mathematically, just trust me on that one. But, so that means, does anyone remember what does it mean whenever there's that sigmoidal shape? What does that indicate from chapter 5? So this will be on the 6th. Does it indicate what? Cooperativity. Cooperativity or allostery, what's the name? Okay. But if we notice, if we go to really, really high substrate concentration, so this is substrate as a function of velocity. When you get to so high concentration substrate, all of the binding sites on that enzyme are bound. So it no longer matters. If we're right here, so you go all the way up, it's way up here. If you add in 5 more micromolar, whatever, of substrate to go up here, it's not going to matter. So at this portion of the curve up here, it's 0 order. That's what that meant word-wise before. And so this, if you think back to calculus or geometry, or I don't know where you guys are on it here, does anyone know what's this line here called? It's an asymptote, and this asymptote is called Vmax, or the maximum velocity. When we're plotting velocity, obviously when we're plotting velocity as a function of substrate or enzyme, the velocity is on the y. If it's going to be maximum, what up the y-axis? Forgot to point that out. So that's there's the answers for that part. So in general, many times, please, I just want to always say, this is an ideal situation under ideal characteristics. I mentioned this. You know, at really low substrate concentrations, you got to bind substrate, but at some point in time, you got so much substrate bound to the enzyme that it no longer matters. So this is 0 order, but this one right here, as you approach as the limit of So if you think back to calculus, as the limit approaches 0, or as this approaches 0, this right here is a first order rate. Okay. Please note, it's not always true. Sometimes, like ATCase, it could be second order or third order, depending upon the fact that it's no longer linear index. And so they give this term Michaelis-Menten or steady state kinetics. So Michaelis-Menten is only true under what's called steady state. It's supposed to be an S, I'm sorry. But you may have heard that, or since you're supposed to be working on your papers, and I'm sure you all are, working diligently, you may have read some of these things. And we're going to be starting on Friday, which you not want to miss. We're going to start to talk about what that really indicates, what that means, steady state, and under what conditions. And in particular, I'm hoping through Friday to get to what's called KCAT, KM, and KCAT over KM, and why they're important, okay? And so this is why it's just saying the same thing. Technically, they also call this first part pseudo first order, because it's not a true first order. You just have enzyme and substrate coming together, it should be second order. So don't, in your papers, if you're reading and they say, well, under pseudo first order conditions, that just means it's on this part of the curve, okay? It's where substrate concentrations are relatively low. And in vivo, there are different times. You can imagine, we have some parts of our body where maybe it's under, the reaction's under really high concentrations. Then we have times whenever the substrate concentrations are really low. So the enzyme that's affiliated with that metabolic pathway could be under this portion of the curve. All right, are there any questions?